As we look at the performance and capabilities of these model under controlled testing circumstances, there are two kinds of questions that I'd like you to keep in mind. One of them is a technical engineering-oriented question, which is, what are the generalizations that these particular models seem to be learning? And you may recognize this picture. This is from the movie Arrival, and this is a story where aliens come down to Earth and communicate in some form, and it turns out that the communications are understandable according to principles of linguistics. This is actually a very respectable movie scientifically, especially for an area like linguistics. And it was certainly very fun for me to watch this movie. So that's the technical question. But at the same time, there's a theoretical question, which is that this is a picture of a very different type. This is a caregiver teaching a child. She's reading to the child and thus communicating using language, and is probably not explicitly trying to teach the child what is right and what is wrong about the language. The caregiver is just communicating content, meaningful content to the child. This, by and large, is how we learn our native language. And this is what's called positive input data alone. To a first approximation, our linguistic experience is hearing people around us use language in everyday life, and it is evidence of what can be done in a language, not what can't be done. So the input are not negative in the sense that they're negative examples that you learn not to do things from, but they're positive examples that you learn what is possible. And a big challenge in learning theory is how well positive input data alone can guide a learner to the generalizations that underlie a system. This is a problem with learnability. And contemporary models are now powerful enough that we can start to imagine putting lower bounds on the answer to this question. How well would positive input data alone deliver the right generalizations, the right linguistic generalizations, to a generic flexible learner without hierarchical bias of a strong particular linguistic sort? And so we can imagine in a way that the neural language model is sort of playing the role of an alien that we imagine is unfamiliar to us as adults, but might occupy the mind of a child language learner. And we can ask, well, what would a generic learner that can do all sorts of things with all sorts of sequences, but isn't necessarily constrained to just learn language, what would it learn about language from exposure to a reasonable amount of data? And this is going to be the point of view that I want you to keep in mind in understanding a model's linguistic behavior. So let's brainstorm a little bit how to examine a model's behavior in more detail. Actually, this is an area that there's been a lot of work in the last several years. These are some of the papers. This is work in our lab, actually, has focused a lot on this in the last couple of years. And I will start with what is the best known example in the literature in recent years on this, which is subject-verb agreement. And so this is exemplified in the pattern of the following four sentences. The author laughs is a perfectly ordinary sentence of English, nothing spectacular about it. But we could change either laughs to laugh or author to authors. Either of these changes would make the sentence ungrammatical, would make the sentence wrong, because the verb would be of the wrong form given the subject. If we change the author laughs to the author laugh, we have a singular verb where we have a plural verb where we should have a singular verb for a singular subject. If we change the author laughs to the author's laughs, then we have a singular verb for a plural subject. But of course, when we change both, then we wind up with an okay structure again. The authors laugh, we have a plural verb, plural subject. These are simple examples, and surely any reasonable model ought to get these right. In fact, I'm sure you would expect that even a bigram language model would get these right. But we can make things a little harder. For example, suppose we post-modify the subject-noun phrase with a prepositional phrase, like the author of the novels laughs. Now, the most recently preceding noun before the verb is actually of the wrong number relative to the verb. So in this case, we have a singular verb, laughs, but the most immediately preceding noun is plural. And so a heuristic by which the model attended just to the most recent noun, which would actually do the right thing for a lot of examples because a lot of subjects don't have any post-modifying material, that kind of heuristic would get things wrong. That is, that heuristic would incorrectly predict that for the author of the novels, the next word, if it's a verb and if it's a verb form of the verb laugh, should be laugh, that it should be laughs. This intermediate noun, novels in this setting, is called the attractor in the psycholinguistics literature, and that name has been come to be used in the NLP literature as well. And we're going to refer to that later on, the attractor. It is a noun that is in between the head noun of the subject and the verb that the subject is agreeing with. Here's another thing we could do. We could embed the sentence in a complement clause. Readers know that the author laughs. Readers know that the author laugh is wrong. So this would challenge a model that had a different heuristic, which was just memorize the first noun of the sentence and use that number with the verb. That would be incorrect here. It's not an attractor because that word readers is not in between the subject and the verb, but it is something that could be a pitfall for another heuristic. And of course, we can make these situations much more complicated. So for example, readers know that the author who wrote the novels, regardless of what people may think, laughs in unusual circumstances. Laugh would be incorrect here, even though every single other noun in the sentence is actually plural. The noun-verb agreement relationship is one that is characterized by a syntactic hierarchical structure. This is a hierarchical characterization of this sentence, this last sentence that I showed you, which is the grammatical version of it. And in order to determine what the number form of the verb ought to be, you can ask, well, what is the verb phrase that the verb is in? And it's that verb phrase down there. And what is that subject for the verb phrase? And that is a structural relationship. In particular, the verb phrase, if it's inside a sentence, an S, then it should be that the preceding noun phrase inside the sentence. And that is a structural, tree hierarchical structural relationship. And then you can, once you have that noun phrase, you can ask what is the head noun of that noun phrase. And that head noun of that noun phrase, its number ought to be matched by the number of the verb. You notice that once again, in linear distance, this may be a very, very distal relationship. And there may be many other nouns in the sentence with differing numbers, but it is this particular relationship that matters for subject-verb agreement. And this is a classic argument for the hierarchical nature of linguistic structure that goes back at least as far as Chomsky's work in the 1950s. And now there are other hierarchical relationship specifications that are given. So for example, this arrow pointing directly from last to author with the n subj annotation is what's called a dependency relationship. The trees that you can use to represent syntactic relationships in sentences are not always constituency trees like the full-on tree that we drew, but also sometimes dependency trees, which are trees which are just pointers, edges on the tree are pointers from words to other words. In particular, from words that govern the words to the words that are governed. The n subj is the nominal subject relationship, and that's a direct specification of that. So it's an alternative representation that we can use, and there are broad equivalencies between the constituency and dependency representations. They're both okay. So given that setting, we can then formulate a way of testing an incremental left to right neural language model on subject-verb agreement. We have two different versions of the same sentence, like the key to the cabinets is or are on the table. Is would be correct, are would be incorrect given the context. So we separate out the preceding content, we'll call that the context. The next word in either the singular or the plural form of a given verb is the target word. And we can take any incremental language model and we can ask, does the language model put a higher probability on the right form of the verb, given the context, in this case is, than it puts on the wrong form of the verb? Okay, so this approach was pioneered by Linzen et al. 2016. And just to give a couple of examples of the findings that they got with language models of that time, for example, they had a language model trained on some Wikipedia text, which we haven't read here, but they also took that model of Josefowicz et al. 2016 that I described to you. And that's what they call the Google language model. And they found that even that model actually did quite poorly once you had more than one, and certainly more than one attractor. That is, noun phrase intervening between the actual subject and the verb. They also found that if they took an LSTM language model and they trained it not for general next word prediction overall, but solely for the task of verb inflection, then it actually did very well. And much better, in fact, than the language modeling. So in a sense, the model was using, it didn't care so much about verb inflection on its own that it was doing as well as that architecture possibly could. But the gray model, in a sense, manifests the overall performance that you would get on inflection as a side effect of generally changing a language model. So whereas the green line is sort of a more supervised characterization, the gray line is more of an unsupervised, what falls out as a general consequence of trying to learn the patterns in language, what falls out about subject-verb agreement. Another interesting finding that they had is that for the models that were trained, dedicated for the verb inflection task, they did find that the LSTM performed better than the simple recurrent network. Notice there's another sub-result in here, which is that performance when the subject is singular is worse than when the subject is plural. That is that if you have a singular subject and intervening plural attractors, then you're more likely to mispredict that the verb will be plural than if you have a plural subject with singular attractors. And I want you to remember that for a moment, because it's going to be relevant when we connect this to human behavior, which we're going to spend a moment doing now after this break.